Our sun, a giant ball of burning gas. It's the reason for life on Earth. But the sun can also be dangerous. It releases huge bursts of energy. We call these bursts solar flares and coronal mass ejections. Imagine a bomb going off, but thousands of times more powerful. That's the scale of a solar flare. These eruptions happen on the sun's surface. They're caused by the sun's magnetic field lines getting tangled and then snapping. These flares release a lot of radiation. This radiation travels at the speed of light. It reaches Earth in just 8 minutes. Luckily, most of this radiation is harmless. Our atmosphere protects us. But sometimes, solar flares can cause problems for our technology. Deep within the sun, a constant dance of magnetic fields takes place. This dance is not just a simple movement but a complex and intricate ballet that shapes the very nature of our star. These fields are generated by the movement of electrically charged plasma. This plasma, composed of ions and electrons, flows and twists, creating magnetic fields that weave through the sun's interior and surface. Think of it like a giant magnetic soup, constantly churning and swirling. The plasma's motion is turbulent and chaotic, yet it follows the laws of magnetohydrodynamics, a branch of physics that studies the dynamics of electrically conducting fluids. Sometimes these magnetic field lines get so tangled and twisted that they snap, like a rubber band stretched too far. This snapping can release pent-up energy in a sudden and dramatic fashion. When this happens, a tremendous amount of energy is released, resulting in a solar flare. These flares are powerful bursts of radiation that can affect space weather and even disrupt communications on Earth. These flares occur in active regions on the sun's surface, often near sunspots. Sunspots are areas where the magnetic field is particularly strong and complex. Sunspots are cooler, darker areas on the sun's surface that are also associated with intense magnetic activity. They appear dark because they are cooler than the surrounding areas, but they are still incredibly hot by Earth standards. The energy released during a solar flare is equivalent to millions of hydrogen bombs exploding simultaneously. This immense energy can accelerate particles to near the speed of light, creating a cascade of effects throughout the solar system. It's a truly awe-inspiring display of the sun's power. The sun's magnetic dance is a reminder of the dynamic and ever-changing nature of our closest star, influencing everything from space weather to the climate on Earth. The birth of a solar flare is a dramatic event, a cosmic spectacle that unfolds with immense power and energy. It begins with the twisting and turning of magnetic field lines in the sun's atmosphere, a dance of invisible forces that shape the very fabric of our star. As these lines become increasingly tangled, they store vast amounts of energy, like a coiled spring ready to release. The tension builds up over time, creating a potential for a massive release of energy. When the tension becomes too great, the magnetic field lines snap, releasing the stored energy in a sudden, violent burst. This release is both spectacular and powerful, sending shockwaves through the solar atmosphere. This burst of energy heats the surrounding plasma to millions of degrees Celsius, causing it to emit a blinding flash of light. The intensity of this light can be so great that it outshines the rest of the sun for a brief moment. This flash of light is what we observe as a solar flare, a brilliant beacon that can be seen from space. It travels at the speed of light, reaching Earth in about 8 minutes. This rapid journey underscores the immense speed at which these events unfold. Along with the light, solar flares also release a stream of charged particles known as the solar wind. These particles can interact with Earth's magnetic field, sometimes causing beautiful auroras or even disrupting communication systems. Solar flares are often accompanied by another phenomenon known as coronal mass ejections, or CMEs. If a solar flare is like a gunshot, a CME is like a tsunami. It's a massive eruption of plasma and magnetic field from the sun's corona, the outermost layer of its atmosphere. CMEs can contain billions of tons of solar material and travel at speeds of millions of miles per hour. When a CME is directed towards Earth, it can interact with our planet's magnetic field, triggering geomagnetic storms. These storms can have significant impacts on our planet's technology and infrastructure. They can disrupt radio communications, GPS navigation, and even power grids. Section 5. Earth in the crosshairs. When a solar flare or CME is directed towards Earth, it can have a range of effects on our planet. These solar phenomena are massive bursts of solar wind and magnetic fields rising above the solar corona or being released into space. The most noticeable effect is often the aurora borealis, or northern lights. These natural light displays are not just beautiful but also a visible reminder of the sun's influence on our planet. These shimmering curtains of light are caused by charged particles from the sun interacting with Earth's atmosphere. When these particles collide with gases like oxygen and nitrogen, they create the stunning light shows we see in the polar regions. However, solar storms can also have more disruptive effects. These storms can release a tremendous amount of energy, which can affect our planet in various ways. They can interfere with radio communications, causing blackouts and disruptions to GPS systems. This interference can affect everything from aviation to maritime navigation, making it a significant concern for global transportation. In extreme cases, they can even induce currents in power grids, leading to widespread power outages. These geomagnetic-induced currents can damage transformers and other critical infrastructure, potentially causing long-term damage. The impact of solar storms on our technology is a growing concern as we become increasingly reliant on satellites, communications networks, and other space-based technologies. Our modern way of life depends heavily on these systems, making them vulnerable to solar activity. Understanding and mitigating these risks is crucial for our technological future. Scientists and engineers are working tirelessly to develop better forecasting methods and protective measures to safeguard our technology from the sun's unpredictable behavior. Section 6. The 1859 Carrington Event. In 1859, the largest solar storm in recorded history struck Earth. Known as the Carrington Event, it caused widespread telegraph system failures and sparked auroras that were visible as far south as the Caribbean. During the Carrington Event, telegraph operators reported receiving electric shocks from their equipment, and some telegraph systems continued to operate even after being disconnected from their power sources. The auroras were so bright that people were able to read newspapers by their light. While the Carrington Event occurred before our reliance on modern technology, it serves as a stark reminder of the potential power of solar storms and the importance of being prepared for future events. Section 7. The vulnerability of our technological age. In today's technologically advanced world, we are more vulnerable to solar storms than ever before. Our reliance on satellites for communication, navigation, and Earth observation has grown exponentially. A severe solar storm could cripple these systems, with cascading effects on our daily lives. Power grids, which are essential for modern society, are also susceptible to solar storm disruptions. The induced currents from a powerful geomagnetic storm could overload transformers and cause widespread blackouts, potentially lasting for days or even weeks. The economic and societal impacts of such an event would be significant, highlighting the need for continued research, monitoring, and mitigation strategies to protect our critical infrastructure. Section 8. Eyes on the Sun, NASA's Sentinels. Recognizing the threat posed by solar storms, NASA and other space agencies around the world have deployed a fleet of spacecraft to monitor the sun and provide early warning of potentially hazardous events. These space weather sentinels constantly observe the sun, tracking solar flares, CMEs, and other solar activity. They provide valuable data that allows scientists to better understand the sun's behavior and improve space weather forecasting. One such spacecraft is the Solar Dynamics Observatory, or SDO, which captures high-resolution images of the sun in multiple wavelengths, providing insights into the sun's magnetic field and the processes that drive solar flares. Section 9. Forecasting space weather. Just like we forecast the weather here on Earth, scientists are working to improve our ability to forecast space weather. By analyzing data from spacecraft observing the sun, scientists can track solar flares and CMEs and predict whether they might impact Earth. Space weather forecasts provide crucial information to satellite operators, power grid managers, and other stakeholders who rely on space-based technologies. These forecasts allow them to take steps to protect their assets from the potentially damaging effects of solar storms. While space weather forecasting is still an evolving field, significant progress has been made in recent years, improving our ability to anticipate and mitigate the risks posed by our nearest star. Section 10. The importance of solar flare prediction. Predicting solar flares is crucial for protecting our technological infrastructure and ensuring the safety of astronauts in space. Accurate forecasts can give us time to prepare for potential disruptions, such as power outages, communication blackouts, and GPS errors. For astronauts aboard the International Space Station, solar flare predictions are vital. During a solar storm, astronauts may need to take shelter in shielded areas of the station to protect themselves from increased radiation levels. By improving our understanding of solar flares and developing more accurate prediction models, we can minimize the risks and ensure a more resilient future in our increasingly technological world. Section 11, Conclusion: Our Star, Our Future. The Sun is a source of life and energy, but it also poses a potential threat to our technological civilization. Solar flares and CMEs are powerful reminders of the immense power of our nearest star and the importance of understanding and respecting its capabilities. Through ongoing research, technological advancements, and international collaboration, we can strive to live in harmony with our dynamic and occasionally tempestuous star. By unraveling the mysteries of the Sun, we not only gain a deeper appreciation for its awe-inspiring beauty, but also protect our planet and ensure a brighter future for generations to come.